So the primary structure is extremely important, and just one amino acid out of place alters the protein's properties. So a really good example of that is sickle cell anemia, and it replaces glutamate with valine in the hemoglobin molecule. We're going to look a little bit more at that here in just a minute, but that one amino acid, changes everything. So it causes hydrophobic pockets to be exposed on the surface, and then insoluble fibrous chains are formed, because the hydrophobic pockets are now on the surface instead of, kind of tucked away into a group or a pocket. So anyway, it changes a lot of things when the order of the amino acids, are changed. Another thing primary structure plays a role in is proteins in our diet. So our bodies don't store proteins like they do with carbohydrates and fats. 9 of the 20 amino acids are obtained through what we eat. So there's different sources of protein that we can get. Most of it comes from meat and dairy products. But if you're a vegetarian, then you can get your source of protein in other things like legumes or grains. And then if you're not getting enough protein, then you can get a disorder, protein, energy, malnutrition. So anyway, there's things that happen when we're not getting enough protein in our diet. Okay, so now we're going to look at secondary and tertiary structures. So hydrogen bonding really determines a lot of our structures in the proteins. Hydrogen bond occurs between the hydrogen atoms attached to nitrogen and the oxygen atom in the carbonyl group on the backbone. It can also take place between the side chains, the amino acid side chains, or it can take place with surrounding water molecules. So we're going to see that hydrogen bonding plays a big role in our structure. So here's some examples right here. So on the very left, all those pink dots represent hydrogen bonding. So there's several going there between the two sheets. Then we have just a few that kind of bring the peptide together here in the middle. And then on the very far right, you can see there's several hydrogen bonds. So all the pink dots represent hydrogen bonding. So we're going to get, this is a tertiary structure, but we'll get to that here in just a minute. We're also going to be looking at ionic attractions between our groups. So ionic bonds, like disulfide bonds, can form salt bridges. So the salt bridge was right here. So you can see in the middle of the protein, we have the positive amino group there and the carboxyl group, the negative. So because we have a positive and a negative charge, we form that ionic bond. I said disulfide bond. I didn't mean disulfide bond. So just a positive and negative charge can form that ionic bond. We do have disulfide bonds occurring, with cysteine because it has the sulfur, and the hydrogen has that thiol group in there. So we have an example of that down here on the right. The disulfide bond is taking place. Again, all these interactions are causing the protein to form the shape it is in, pulling it together or creating these pockets. We also are going to be looking at hydrophobic interactions between non-polar side chains. So some examples here are in the yellow. All of these side chains are non-polar, so they're kind of huddling there together in this pocket. So all of these play a huge role in the shape of the protein. Okay, so proteins can be separated using their net charges. Okay, if they have a charge, we can separate them using electrophoresis. It's used routinely in clinical laboratories to figure out what type of proteins are present in the sample. I think I have a picture, right here. So the positively charged proteins will go towards the cathode, which is on the left side, and the negatively charged proteins move towards the positive anode. So they use electrophoresis, especially with determining sickle cell anemia. So for normal adult hemoglobin, there's only HbA. So you can see in the orange there, normal. So that's all there would be. Sickle cell anemia does not have HbA. It shows HbS. So that big purple rectangle there. And then if you have traits of sickle cell, then you have both HbS and HbA. So they use electrophoresis to determine the sickle cell anemia. Okay, the secondary protein structure, there's two different structures. We have the alpha helix. Alpha helix is formed by hydrogen bonds forming along the peptide backbone. So we have hydrogen on the nitrogen group, or nitrogen forming a hydrogen bond with the oxygen in the carbonyl group. So it just forms this coil, and there's like 3.6 amino acids per turn in the coil. You can see on the B picture on the very right, it's looking down on top of the coil, and you can see all those R groups sticking out from the peptide backbone. And then we also have, in the secondary structure, we have the beta sheet. So the same interaction is taking place with the hydrogen bonding between the hydrogen on nitrogen and the oxygen on the carbonyl. But here, instead of the coil, it's a flat sheet, and the chain just folds back in on itself. So if you look on the side, on the right side, it says amino terminal. So you have the N terminal there, and then it curves around and goes the other direction. So the C terminal starts on that side as well. So basically, just to show you what I mean here, we have N terminal, and then it comes back around, C terminal. So over here would be C and then N. So it's just kind of folding up on itself. Also, the R, the side chains are either on top of the beta sheet or below the beta sheet. So in that bottom picture, you can see the R's either sticking up or down from the beta sheet. So these are the two structures that are possible in a secondary protein structure. So you either have the alpha helix or the beta sheet. Proteins can either be fibrous or globular. So fibrous proteins are really tough. They're insoluble, and they're in the forms of the fibers or sheets. So, for example, wool, hair, and fingernails are all made up of fibrous proteins, keratin, and they're formed the alpha helices, and then they twist together, and then they twist into larger bundles, so it makes them very, very tough. And the hardness and the flexibility and the stretchiness of the material varies with how many disulfide bonds are present. So the disulfide bonds play a role here in the fibrous proteins as well. And then we also have, so those are in the alpha helix structure. And then we also have some fibrous proteins that are in the beta sheets. So natural silk and spider webs are made of fibrin, and they are in these beta sheet stacks. The R groups in these are pretty small because you have glycine and alanine. So glycine has the hydrogen side chain and alanine has the methyl side chain. And so they're able to stack pretty tightly because the hydrogens will be on the same side of the stacking, and then the methyl groups will be on the same side. So they're able to stack pretty tightly. So these are all fibrous proteins. Again, they're just very tough and insoluble. Now, globular proteins are soluble, and their shape is a lot different. So fibrous proteins were just the alpha helix, or the beta sheet. But with globular proteins, they have the tertiary structure. So their structure depends on the interaction between the R side chains. So again, that's going to be the hydrogen bonding, the salt bridges, the hydrophobic interactions, disulfide bonds. So all of those are going to be determining the shape of the globular proteins. So since it's water soluble, the hydrophilic side chains are going to be on the outer surfaces of the globular proteins. That's what makes it soluble in water. That way they can travel through body fluids. Okay, so bringing us to tertiary structure here. So tertiary structure is the way where an entire protein chain is coiled and folded into a specific 3D shape. So there's not a repeating structure like the secondary structure was. It's kind of all over the place depending on what the R groups of the amino acids are. So again, we'll have all those bonding taking place that I was talking about with hydrogen bonding or hydrophobic interactions or ionic bonds, disulfide bonds. So all of these are going to play a role in how the amino acids and the protein are going to form this tertiary protein. Oh, one more thing. The native protein is just the shape of the protein in living systems. So that's always important to know. So this is an example of a tertiary protein. So we've got an alpha helix, we've got beta sheets, we've got connecting loops and disulfide bonds and hydrophobic pockets there. And so there's all kinds of things going in on the tertiary structure. Again, it's just kind of all over the place. Tertiary structures can also have conjugated proteins, and conjugated proteins are proteins that are aided in its function by one or more non-amino acid units in the structure. So for an example, myoglobin here, so that's the picture represented in AOB. Myoglobin has a heme group embedded within the polypeptide chain, and that's that red. So on A up there, that's that red portion. Also in B, that's the red portion. That's the heme group that will carry the oxygen and myoglobin. So we're going to look at, in the next structure, we'll see iron within one of the protein structures. So anything that's not part of the amino acid would be considered a non-amino acid unit, and then it would be considered a conjugated protein.